Fine. Now let us see this question. He gave the question as the network shown below has a resonant frequency that is 150 kilohertz and bandwidth of 600 hertz. 600 hertz, and he is asking for Q factor. Right. This was a GATE 2022 question actually. So now let us see generally what is Q factor first. Q factor. What is Q factor? Q factor can be defined as in overall full cycle, that is 2 pi into maximum energy stored divided by energy dissipated per cycle. Right. So Q factor can be defined as 2 pi into maximum energy stored divided by energy dissipated per cycle. So here we need storage, energy storage element as well as energy dissipating elements. Right. We need both the things in order to find Q factor. Right. And here as per the circuit given, it is a parallel RLC circuit. Right. Now what we have to do? We have to create a generalized formula. Between resonant frequency, Q factor and bandwidth. Right. We have to create this. We have to create a relation now. Right. So this is the base formula we got. Right. The base formula is Q factor is equal to 2 pi into maximum energy stored divided by energy dissipated per cycle. Now let me take some examples. Let me take a resistor. Now what is the Q factor for this? 2 pi into, does energy is stored in resistor? Is energy stored in a resistor or not? No. So energy stored is 0 and there will be certain energy dissipated. So we don't know what is the thing. So let it be some x. Now the answer will be 2 pi into 0. So answer will be 0. So for a purely resistive circuit, it should be Q factor should be 0. Then for purely inductive or purely capacitive circuit, what is the Q factor? 2 pi into maximum energy stored. So these are energy storing elements. So energy stored in inductor will be half Li square divided by what is the energy dissipated? There is no any element for dissipating energy. Right. So energy dissipated will be 0. Actually generally energy storage elements are inductor and capacitor, whereas energy dissipating element is resistor. So here it is purely inductive circuit and here it is purely capacitive circuit. I'll write that equation also. 2 pi into half CV square, energy stored in capacitor is half CV square divided by energy dissipating. We need energy dissipating. What is the energy dissipated? 0, because there is no resistor here. So here also it is 0. So Q will be infinity. Right. In the same way, I'd like to go to series RLC circuit directly. From there, we will be getting a common relation among all the parameters given. Right? R, L, C. So here Q factor, generally it is defined as reactive. I mean, if you want to write directly, we can write it directly. So it is directly written as reactive impedance divided by resistance, or reactive component divided by active component. What is reactive component here? Inductor and capacitor. Both are reactive components. So we need reactive component divided by active component. What is the reactive component? For example, now I am considering the case of inductor. Now reactive component by active component. Reactive component is XL and active component is R. So it can be written as omega L by R. Right. This omega is resonant frequency. This omega is resonant frequency, and this can be modified as omega naught divided by R by L. Now, right, we can modify this as omega naught divided by R by L. Now, one more thing is, let me write the lower cutoff frequency and upper cutoff frequency for this series RL circuit. Right. For series RLC circuit, the lower cutoff frequency will be minus R by 2L plus root over R by 2L whole square plus 1 by LC, and upper cutoff frequency will be R by 2L plus root over R by 2L whole square plus LC. Now, the difference between upper cutoff frequency and lower cutoff frequency will be called as bandwidth. We generally know this, right? We generally know the difference between, suppose if the curve is like this, and if this is the lower cutoff frequency and this is the upper cutoff frequency, then the difference between lower cutoff and upper cutoff frequency, or upper cutoff minus lower cutoff frequency, will give bandwidth. This zone is called bandwidth zone, right? So, bandwidth. Now, what is the bandwidth from here? It will be R by L. R by L directly. R by 2L minus R by 2L it will be. So, after simplifying, it will be R by L directly. Because this component will be cancelled actually. If you do omega 2 minus omega 1, this component will be cancelled and these two will get added. Right. That is how we got bandwidth as R by L. So, we can write this as omega naught divided by omega 2 minus omega 1. So, therefore, Q factor can be written as resonant frequency divided by bandwidth. This is a generalized formula. This is generalized formula, valid everywhere. For any resonant circuit, it is valid. Now, coming to the question, they gave it as resonant frequency is 150 kilohertz. Resonant frequency is 150 kilo, so 10 cube divided by, and bandwidth is 600 hertz. Bandwidth is 600 hertz. So if we simplify, 150 ones are 150 fours are. So it is 1000 by 4. It will be 250. Now, what is the unit of Q factor? What is the unit of Q factor? Here, if you see clearly, in the numerator it is energy and denominator also it is energy. So energy by energy. If we consider in the above it is kilowatt hour, in below also it is kilowatt hour. Both will get cancelled and the unit for Q factor will be no unit or dimensionless. So Q factor is a constant term. It has no unit. It is just defining maximum energy stored divided by energy dissipated per cycle in a complete cycle. In a complete cycle. Right. This is the brief explanation about Q factor and the relation between Q factor, resonant frequency and bandwidth. Right. Hope this concept is clear. I will come with a new concept. Thank you.